morning. This is your 10th number of digital class for the subject physics and the first number of digital class for the chapter electrostatic potential and capacitance. It comes under the unit electrostatics. Now here we are going to discuss two topics. One is your electrostatic potential energy, another one is your electric potential, and after that we will go few numericals. Now before discussing this topic electrostatic potential energy, let me go for this figure. Now you see this figure, what this figure define. You do have a source charge plus Q. Definitely if you have a charge in an influencing region creates surrounding that charge, and this influencing region is nothing but the field. So here the field is your this circular region which we define as a field. Now if you place any charge within this field, what will happen? That charge get experience force. If we place any charge out of this field, then no force get experience on that charge. So here we have considered 2 points A and B, so well within the field. Now if we place a charge Q naught at A, so definitely a repulsive force will get experience. It means the source charge will not let the test charge to place it at A, because both have the positive, and source charge is of higher magnitude than that of the test charge. So if you want to place at A this test charge, you have to do work against this repulsive force. And if you waste certain amount of energy in doing work, that energy gets stored on the charge as is potential energy. So this part we are going to use it in our topic, that is your electrostatic potential energy. Now here you see what it says: electrostatic or electric potential energy of a charge at a point in the electric field due to any charge is defined as the work done by an external force in bringing a test charge from infinity to that point in the electric field. Now here you see practically infinity you can't define. So see this figure and see the definition: electric potential energy of a charge. Which charge is here? This one. This is nothing but is a test charge. And at a point, it may be B, it may be A, because A and B is well within the field of the source charge. Due to any charge is your what? That is your source charge. At a point in the electric field due to any charge. Electric field is due to your source charge. So this charge is your source charge. Is defined as the work done by an external force. So definitely both are the positive charge, and this magnitude is higher than this one. So definitely a repulsive force will get experience on this test charge, which is in higher magnitude. Is defined as the work done by an external force in bringing a test charge from infinity to that point in the electric field. So as practically infinity you can't define, that's why we have considered in the figure two finite points, that is your A and B. So let me consider already a test charge is on the point at A, which is well within the field, and you have to move this test charge from A to B. So definitely this is positive, so repulsive force will be there. So if you have to move this test charge plus Q naught from A to B, then you have to do work against this repulsive force, and doing work is nothing but wasting of certain amount of energy, and that energy gets stored on the charge as is potential energy. So if you have to define potential energy at B, what you have to do? You have to bring a test charge from infinity and you have to place it at B. And for that, how much work you have done? That is nothing but the potential energy at B. So practically infinity you can't define. That's why I consider two finite point A and B. And theoretically what we will do? We will consider A as your infinity and B is the specific point where we have to define the potential energy. So if we place a charge plus Q naught at A, so force will be there from the definition of the field intensity, F vector equal to Q naught E vector. Now work done against this force, so force is repulsive. So if you have to move this test charge from A to B, then you have to do work against this repulsive force. So dr is your from A to B and F is your from B to A, so they are in opposite direction. So if you have to find the work done against this force F vector in moving the charge Q naught from A to B, then dw equal to F vector dot dr vector. So F dr cos 180 degree, so cos 180 degree minus 1, so it comes out to be your minus F dr. So if you substitute the magnitude, then it becomes minus Q naught E dr. So this is your work done to move the test charge from A to B, and A and B is your well within the field of the source charge plus capital Q. So as per the definition, if you have to define the potential energy at B, what you have to do, you have to consider A is your infinity. So you see this one, electrostatic potential energy of the test charge plus Q naught within the electric field of the source charge plus Q is defined. Electrostatic potential energy of the test charge plus Q naught within the electric field of the source charge plus Q is defined. So electrostatic potential energy we are trying to define at the point B. So what you have to do, you have to integrate, because infinity you can't define. This is the work done to move the test charge from A to B. So if you have to go for the electrostatic potential energy, then you have to consider A is your infinity and B is the specific point where you have to define the electrostatic potential energy. So you have to go for the integration, that is infinity, from infinity to B. You are bringing the test charge from infinity to B, and that amount of work can be defined W equal to integrating this part, infinity to B Q naught E dr. So this is your expression for the electrostatic potential energy. Now let me go for this topic, electrostatic potential or electric potential. This one is your electrostatic potential energy and this is your electric potential. Now see the definition and see this figure. This is your source charge and A and B 2 points as previously. Now here we have placed what? Plus Q naught at A, and what we have done here, we have placed plus 1, that is your unit positive charge, not the Q naught. Q naught may be any value other than unity, or it may be unity in case of potential. So here the value is your Q naught plus Q naught, and here is your plus 1, and the diagram is almost same. Source charge, source charge. So it says that electric potential at a point in the electric field is defined as the work done in moving a unit positive charge from infinity to that point in the electric field of the source charge. So here we are trying to define potential at P, which is at a distance r from the source charge, and for that we have considered 2 points A and B. At A we have placed a unit positive charge, and we will bring this unit positive charge from A to B, and we will define the work done, and later on we will integrate to define the potential at P. Now you see, if we place a unit positive charge at A plus 1, which is at a distance x, then the Coulomb force will be your F plus capital Q plus 1 x square. So kq by x square. K is your value, 9 into 10 to the 1 9. So work done to move the test charge plus 1 from A to B is your repulsive force is this side, and AB towards this side. So cos 180 degrees. So it comes out this one. Now as per the definition, it says that electric potential at a point in the electric field is defined as the work done in moving a unit positive charge from infinity to that point in the electric field of the source charge. So here experimentally infinity you can't define, that's why you have considered 2 finite point A and B, and we have calculated the work done. Now this work done is nothing but is your minus kq by x square dx. So if you have to define potential at P, what you have to do, you have to go for this definition and you have to integrate considering infinity to r. So if you integrate this expression, electric potential at P, to define electric potential at P, you have to integrate this expression, that is potential is denoted basically by V, and it goes for the work done infinity to r. So minus kq will comes out of the integration sign, infinity to r, x to the power minus 2 dx. So I think all of you know this formula, integration after integration, that is your formula, x to the power n dx equal to x to the power n plus 1 by n plus 1. That formula we have used here, minus kq, x to the power minus 2 plus 1 by minus 2 plus 1 infinity to r. So minus 2 plus 1 is your minus 1, so minus minus goes off, kq, then you have to 1 by x infinity to r. So you have to substitute upper limit minus lower limit. So v equal to kq by r. 1 by infinity is your what? 0. So this is your one topic, electrostatic potential energy. Another one is your electric potential. Now let me go a few numerical. Let me consider this numerical. Calculate the electric potential at a distance of 9 centimeter from a charge 4 into 10 to the minus 9 coulomb. So you see, given this formula we are going to use kq by r. So q is your 4 into 10 to the minus 9 coulomb, r is your 9 centimeter. Always you have to convert it in amperage system. 9 into 10 to the power minus 2 meter. So potential is your kq by r. If you substitute, you will get 400 volt. On simplification, 9 goes off, plus 9 and minus 9 exponent goes off, so 10 to the minus 2 up to 100, so it becomes 400. So again, calculate the work done in bringing a charge 1 into 10 to the minus 9 coulomb from infinity to a point distance 3 centimeter from a point charge 2 into 10 to the power minus 6 coulomb. So again, you have to use this expression. In potential work done, you have got kq by r considering unit charge. So if you consider in place of unit this test charge q naught, so it comes out to be your this formula kq by r. So if you substitute this formula here, 9 into 10 to the power 9 k value, q is your source charge which in bringing a charge, this is your test charge, and this is your source charge 2 into 10 to the minus 6, 1 into 10 to the minus 9, and distance is your 3 centimeter, 3 into 10 to the minus 2. So we will get 6 into 10 to the power minus 4 joule. So if you simplify this one, 339, 3 to 6, and 10 to the power 9 to the minus 1 goes off, so 10 to the power minus 4 joule. Now potential basically a scalar quantity under the note if you go for this part, and potential is your work by charge, work done per nature. So work is nothing but is your potential into charge. So that's why we have multiplied by the test charge to define the work, potential into charge. Now SI unit is your for potential is your joule per coulomb or volt you can say, and dimension for potential is your again this formula, work is your m1 L2 T minus 2 and charge is your AT. We have discussed in previous class chapter 1, m1 L2 T minus 3 A minus 1. So you please go for this definition. Again I am repeating, it says that electrostatic potential energy, the definition is your electric potential energy of a charge. This charge is your test charge at a point in the electric field due to any charge. This is your source charge, is defined as the work done by an external force in bringing a test charge from infinity to that point in the electric field. Now electric potential, you have to replace that test charge by unit positive charge, and rest part is same. So go for this topic and find out your doubts and repeat the topics. More you repeat, more it becomes clear. Thank you.